All right, hi everyone. Welcome to the lecture this evening. Thank you all for coming. We're going to be talking about volcanoes and particularly volcanic gases and how they interact with the environment around us. As I was putting together this lecture, I was thinking about when I was back choosing the path for me to follow. I'd always been interested in volcanoes. I was very fortunate when I was around 6 or 7 years old to get to visit a volcano, and it stayed with me for many, many years. But I remember what I struggled with was relating what I was learning in my chemistry classes or my physics classes to a career, a pathway, something that I would study and feel passionate about. So what I want to show you today is some of the ways that chemistry can be applied to help us understand volcanoes. There'll be a little bit of physics in there as well. That's the joy of earth sciences. It's a little bit of physics, a little bit of chemistry, a little bit of biology. It's a bit of everything. So next slide, please. I want to start off with the bigger picture. So we hear often on the news and the media that, the news and the media about big volcanic eruptions that impact on our atmosphere, on societies. You may have heard about the recent Tonga eruption that really captured the hearts and minds of people globally. But what is important to think about is that actually volcanoes are a really crucial part of the whole Earth system. They are central to how our planet has evolved since it first formed, and they're absolutely essential to how our planet has become habitable. Next slide, please. So they form a really important part of global geochemical cycles, such as the carbon cycle, which helps to regulate our climate. Now, they are the main pathway by which elements such as carbon are transported from the mantle deep within our planet through the Earth's crust and out into the atmosphere. And similarly, at places such as subduction zones, which I'll speak a little bit more about later on, where one plate is being dragged beneath the other, and this causes volcanoes. This is a really important location where elements such as carbon are recycled through volcanoes and back into our atmosphere. And volcanoes also contribute essential nutrients to our atmosphere and our surface environment, such as iron. You may have seen pictures where when a volcanic eruption happens and the gas plume moves out over the ocean, you see these beautiful, colorful algal blooms happen. This is because iron has been deposited out of the gas plume into the ocean. And iron is a really limiting, important nutrient for microbial growth, small multicellular life. So the algal blooms will suddenly flourish because the volcanic eruption has fertilized this portion of the ocean. So there are many ways that volcanoes have a positive feedback relationship with our planet. Next slide, please. But we can't escape the fact that in our current very highly populated, globalized society, volcanic eruptions can have a huge array of very devastating impacts. Now, these are just a few examples of the kind of volcanic hazards that we have to think about when managing an ongoing volcanic crisis. So we have to think about the impact of volcanic ash. These is very tiny particles. They're essentially glass fragments. If you look at them under a microscope, they're very sharp, very abrasive, and they can also, close to the source of the volcano, bury homes, cars, up to thicknesses of several meters. These poses a respiratory hazard as well for local communities, so it's important that they protect themselves with proper respiratory protection. Gas emissions, which is my personal speciality, is potentially the silent killer. Now, I call them that because these gas emissions can persist over years to decades at relatively low levels. So we're not talking very explosive eruptions. This is an example from Nicaragua in Masaya. Other way around, Masaya in Nicaragua, which is an open lava lake releasing gases passively all the time. But for local communities, they're exposed to these toxic gases continuously. So actually looking at the long-term health implications of this persistent degassing is very important. Lava flows are a very obvious hazard. This is a picture from the recent La Palma eruption. You'll hear more about that in a couple of slides' time, but they will pretty much bulldoze everything in their path. And then probably the most catastrophic, but fortunately confined to the very proximal region around volcanoes, is pyroclastic flows. And these are superheated clouds of ash and gas which race at hurricane speeds down the sides of volcanoes. Now, really the only protection against a pyroclastic flow is timely and effective evacuation. All right, next slide, please. So when we think about living with volcanoes, probably 9 times out of 10, the example that people bring to mind is that of Vesuvius volcano and the city of Naples. The city is home to around 2 million people, and we know from Vesuvius's eruptive record that it's had a very explosive past. And evacuating 2 million people, if we detected unrest, would be a very non-trivial task. So there's huge concern that if Vesuvius was to return to styles of activity it's shown in the past, then we would have a very major problem. So this is one of the most well-instrumented volcanoes in the world. Next slide, please. At the other end of the spectrum, we have La Palma in the Canary Islands. Now, rather than having a very large explosive eruption, although this eruption did produce a lot of ash, its main hazard was lava effusion. And you can see this is a photo from just a few days into the eruption. We already covered a significant proportion of homes. Eventually around 3,000 homes were destroyed and 7,000 people displaced. So this has had a huge and long-term impact on the communities on the Canary Islands. So just 2 examples of very explosive and then less explosive, but still no less hazardous volcanoes, to put into context why it's important to be understanding these natural hazards. Right, next slide, please. Ooh, one back. One backwards if possible. Awesome. Okay, so today we're talking about chemistry, and there are 3 questions we're going to think about. We're going to think about how magma chemistry influences the eruptive style, so the explosivity. We're going to think about how we can use chemistry to monitor volcanoes before they erupt. And then what are the environmental chemical hazards when the volcanoes do erupt? All right, next slide. So there are around 1,500 potentially active volcanoes in the world at any one time. Around 500 of those have erupted historically, and at any point in time, we can expect around 30 to 50 volcanoes to be active. So now there's between 30 and 50 volcanoes having some form of eruptive behavior right now. The simulation that you see on the right-hand side, it's not a simulation, it's actual data, the animation. This is from the Global Volcanism Program. I've put the web address in the bottom. I thoroughly recommend you check this out. It's a fantastic resource. But essentially this shows all volcanic eruptions and earthquakes through time. You can go back as far, I think, as the 1950, and you can see how they're distributed around our planet. And already you can start to see that they concentrate in particular locations and form chains that make out particular outlines. Next slide, please. And these lines correspond to the tectonic plates. So you may well have covered this already in some of your classes, but essentially at the surface of the Earth, we have the crust, and this is divided into tectonic plates, which you see in this map here. And these plates are in constant motion. They move relative to each other, sometimes rubbing up against each other sideways. And sometimes we have this process called subduction, where one plate is dragged beneath the other as 2 plates are forced together. Now, whether the plates are moving apart or moving together, this kind of relative motion leads to these chains of volcanoes. I could probably have a whole separate lecture on exactly how volcanoes are formed. So maybe that's an idea for the next one. But for the moment, we'll focus on the fact that this is kind of the distribution of volcanoes that we see. And then what can we learn from looking at their chemistry? Next slide, please. So not all magma that erupts at the surface is created equally. They all have very different chemistries, different compositions, and this influences the style of the eruption you'd see. So whether it's explosive or effusive. So if we look at this diagram on the right-hand side, they all have very intriguing names like basanite, tephrites, basaltic trachyandesites, a whole lot of words you don't need to understand at the moment. But essentially, the take home here is most primary melts from the mantle. So most what we call primitive magmas start out as a basalt, so down here. And then as magmas rise through the crust, they begin to cool and they crystallize. They form different mineral phases. And as they crystallize, they change their chemical composition. And this change drives the magma along the direction of this red arrow. So from basalt to andesite to dacite and eventually to rhyolite. And the important thing here is that this process that we call fractional crystallization has a big effect on the silica content, the SiO2 content of our magma. And SiO2 is it affects the polymerization of the magma. So it forms chains, and the more silica you have, the stickier your magma gets. And we call that viscosity. So it increases the viscosity of your magma by increasing your silica content. Next slide, please. One back, please. Perfect. And viscosity is really important for understanding this link between magma chemistry and eruptive style. So I just said that the viscosity of the fluid, and the magma here is the fluid, affects how it flows. So if I was to pour water down a slope, it would flow very fast. You can probably all picture that. If I was to pour honey down the same slope, it would move much slower. That's because the honey has a higher viscosity. And this is important for volcanic eruptions because it affects how easily the magma can flow, and it affects how easily the gas can escape. So all magmas have gases like carbon dioxide and sulfur dioxide dissolved inside them. And what is really crucial for fueling explosivity is how quickly this gas can expand as the magma moves towards the surface and decompresses. If you've got a very high viscosity magma, it's much more difficult for this gas to expand, so you can build up the pressure. So generally, the higher viscosity, the more explosive that volcano will be associated with. And we can see from the plot on the bottom here, if we've got temperature along the bottom and viscosity along the y-axis, that your rhyolites and your dacites are orders of magnitude more viscous than your low viscosity basalts. So a basalt you might associate with somewhere like Hawaii. You've got a lot of lava flows, lava fountains, whereas your rhyolites are going to make your big explosive eruptions. All right, next slide, please. So I've moved on to this already, but essentially this is describing what I was just saying. So on the left-hand side, we have your example of your Hawaiian eruption. We've got these very fluidal fountains. The magma behaves more like water. But actually, if you go towards the higher viscosity end, your fluid starts to behave very differently. It no longer behaves like a fluid. It starts to behave brittly. So if you were to smash a window or smash a glass, that's brittle breakage, brittle fragmentation. And this is how we create all the fine-grained volcanic ash that you see in these big explosive eruption clouds. The gray color is because of all the fine-grained ash. And this is due to brittle fragmentation. Again, I won't go into too much detail because that's bordering on the physics side of things. But magma chemistry matters for governing whether you're going to have a lava flow producing volcano or an explosive climate influencing eruption. All right, next slide, please. The magma viscosity also matters for volcano shape. So you can tell a lot about a volcano's history and what kind of eruptions it has just by looking at it. So I've put two examples here. We've got Mauna Loa in Hawaii, which formed really low angle shield over around 180 kilometers from one side to the other. It's huge. And then we've got Mount Fuji in Japan, which is a really classic example of what we call a stratovolcano. So your characteristic triangular shaped volcano. And this is due again to the differences in viscosity and eruptive style. If you erupt lots of very fluid lava flows, they'll travel a long distance away from the vent, build up the shield volcano style on the left. Whereas if you've got much more sticky, viscous lava, you'll have layers of lava, but also what we call pyroclastic deposits. And pyroclastic refers to basically anything that's fragmented brittly out of the volcano, mostly volcanic ash, and you'll form these very steep-sided stratovolcanoes. Right, next slide, please. So I'm going to shift gear a little bit and think about what is in a volcanic plume. So my research speciality is volcanic gases and how these gases drive eruptions and then how they impact on society and our environment once the gases are emitted to the atmosphere. But volcanic plumes, which is pretty much mostly the gas that comes out of the volcano, has a few more things inside it. So let's have a look at what's in a plume. Mostly it's what we call the volatile gases. Volatile, you'll hear me refer to this a few times. It's basically any element that prefers to go into a gas phase. So it will be dissolved in your magma at depth, but then as soon as it can, it'll quickly leave the magma and go into the gas phase. That's what a volatile is. Mostly it's water vapor, a lot of CO2, a lot of SO2, and then sometimes you have some H2S, which if you've ever been near a volcano that smells like rotten eggs, that's probably the H2S, the hydrogen sulfide you're smelling. We have all these fragments of volcanic ash, which are essentially glass fragments, and give the plume the grey colour. But then a lot of metallic elements. This is much more lesser known and is a really active field of my own research at the moment. So you're hearing hot off the press information here. Volcanoes also release lots of lead, copper, bismuth, heavy metals that you don't necessarily want to be either breathing or incorporating into your agriculture and your food and water supplies. So we'll be touching on the environmental impacts of these metallic elements later on. Next slide, please. Volcanoes can outgas in two different ways. We have our passive degassing and our explosive degassing. I mean, they're fairly self-explanatory terms, but essentially the passive emissions are continuous, low-level emissions that happen over long periods of time. So when we discussed Messiah in Nicaragua a few slides ago, that was an example of a passively degassing volcano. It's not explosive, but it's always releasing gases like a chimney. Whereas explosive degassing happens much more sporadically, but very transiently. So you may have very acute, high impact effects, but generally they don't last beyond a relatively short period of time after the eruption. Next slide, please. When we think about the global budget of total emissions, so I've been involved recently in projects where we've tried to assess what is the total amount of SO2 and CO2 released by volcanoes globally in the present day. It's important to be distinguishing between explosive and passive degassing. Now, from satellites, we can identify what are the strongest SO2 sulfur dioxide emitters on Earth. We've got a map on the bottom here, and then if you prefer graphs, we have a graph on the left-hand side. And actually what we see is that these passive emissions around 10 times more gas than is emitted during explosive eruptions. So if we're interested in what is the total amount of gas released by volcanoes, actually it's these low level but persistent volcanoes that are by far the most important. When we think about the environmental impacts, it reverses. Next slide, please. If we think about how much gas is emitted by volcanoes every year, though, let's put this into a little bit of context. So currently, best estimates suggest around 27 megatons per year of SO2 and 51 megatons per year of CO2. On its own, those numbers probably don't mean a whole lot to you. But if I say that 36,000 megatons per year of CO2 comes from burning fossil fuels for energy and cement production, it puts into perspective the role of volcanoes versus what human activity is doing to our planet. You can also see this clearly in the pie charts on the left-hand side. Volcanic forcings are dominated by anthropogenic emissions. So what we're currently doing at the moment is far greater than volcanoes have ever done to our planet in the past. However, if we put the very recent period of human activity aside, volcanoes are absolutely critical for modulating climate over geological timescales, over thousands to millions of years. And they are a very important source of CO2 and SO2 to our atmosphere and oceans. Next slide, please. All right, shifting gear one more time to think about volcano monitoring and how we might use chemistry in our volcano monitoring. So here I've just put a few examples of the kind of techniques we use to take the pulse of a volcano. We can look at how the ground is deforming. Is it inflating, deflating? How many earthquakes are happening? What is the chemistry of the gases coming out at the surface? We can take geophysical measurements such as gravity or magnetics to look at where magma might be being stored in the subsurface. And we can look at the chemical composition of previously eruptive rocks. We call this petrology. And you can learn a lot about looking at the chemical properties of previous rocks. But we're going to focus today on the gas emissions. Next slide, please. So explosive eruptions, I already mentioned this, they're predominantly driven by bubbles of gas trapped within the magma that build up pressure, cause the magma to expand quickly, and this drives the explosivity. This is a scanning electron microscope image of a pumice fragment. If you've ever held a pumice in your hand, you can feel it's very, very light. This is because it's full of bubbles. And a scanning electron microscope allows you to look in detail about things about the size of the tip of a needle. So yeah, each of these bubbles is smaller than you could ever see by eye. But these pumice fragments form honeycomb-like structures as the gas is expanded very, very quickly within the magma and then cooled quickly to preserve the bubbly texture. Next slide, please. But where the chemistry comes in is that how these gases come from being dissolved within the magma into a gas phase is all dependent on their chemistry and particularly by their solubilities. So I mentioned before the main gases are carbon dioxide, sulfur dioxide, and water. And each of those have a different solubility within magma, or silicate melt, if we're going to be exact about it. And these solubilities are highly pressure dependent. So if we visualize, you can use this cartoon in the middle to help you visualize if you like. As your magma starts to rise towards the surface of the earth, I won't go into the reasons why it might start to rise. Again, that would be a whole nother lecture. It releases the pressure. So we call that decompression. So CO2, carbon dioxide, is the least soluble gas in magmas. So it really wants to come out of solution. And so as you rise towards the surface, your first gas formed will be CO2. As it then rises a little bit more, you then start to get SO2 and then water. So we can actually exploit these changes in solubility. We can model what we would expect to see at the surface for an ascending magma, and then we can compare what we measure. We can actually go in the field and measure it to what is predicted by these models. So we can start to think about, okay, at what pressure is our magma being stored at any one time? And crucially, is it rising? So an example of one of these models is shown on the left-hand side. You can see that as a function of pressure on the y-axis, the amount of carbon dioxide and water dissolved in the melt changes. So at a pressure of around 100 megapascals, we start to see the main drop off in the amount of CO2 dissolved within our magma. And that means it's going into the gas phase. From a practical perspective, when volcanologists like me would go to a volcano and measure the gas that's coming out, we would be measuring ratios like this carbon to sulfur ratio. So we're now looking at the plot on the far right, where CO2 to SO2 is along the x-axis. And this is probably one of the best indicators for changes in activity, for new magma entering the system at the bottom and then starting to rise through the crust. So if we see a change in the carbon to sulfur ratio, then we start to really pay attention and potentially bring in some additional monitoring techniques like seismology for earthquakes and look at the ground deformation. Generally, the strongest way we can monitor volcanoes is a multi-parametric approach. So we bring in chemistry, we bring in physics, and we always bring in modeling. All right, next slide, please. So this is an example from Villarrica in Chile. Its background activity is a very passive lava lake, just like we saw at Messiah. But then in 2015, it had this very explosive eruption. We call this a paroxysmal eruption. And we actually saw this coming in the gas data several weeks ahead of time. So very fortuitously, a permanent monitoring station for gas had been installed about 3 months prior to the start of this eruption. So we were able to characterize background activity. And then even when the emission rate, the total amount of gas was at background levels, we saw this crucial change in the chemistry to a high carbon to sulfur ratio, suggesting that new magma had entered into the magmatic system. Then this was subsequently followed by an increase in the flux of gas at the surface, the emission rate. But we were able to preempt this eruption by several weeks. And you can see some of these data presented in the graph in the center. So this is now a very well-established monitoring tool, particularly for basaltic style volcanoes, where the solubility behavior of volatiles is very well understood. Next slide, please. Just as an aside, how do we actually collect the gas emissions that we use for monitoring? Well, the most traditional approach would be to go there and sample it by hand. This is what we call direct sampling. The image on the left-hand side shows my colleague Brendan McCormick taking a gas sample in Papua New Guinea. Obviously, when the volcano is showing high unrest, this is probably not the place that you'd want to be. So this is where the satellite era has really revolutionized our ability to monitor volcanoes from space. So SO2 is currently the only reliably detectable gas species, but even that can give us a lot of information. So we use satellites a lot. Can you click forward, please? But my area of research is developing the use of drones to try and bridge the gap between these two approaches. Now, satellites are fantastic, but there is a lot of atmosphere between your volcano and the satellite. So this results occasionally in very high uncertainties, and it's not possible to detect all the gases that we need to. So drones are allowing us to take our gas samples directly from where they need to be, but allowing us to remain from a safe distance. So these are increasingly being integrated into volcanic crisis response efforts. Next slide, please. So thinking a little bit about large explosive eruptions, I realize time is passing faster than I expected, so I'll try and keep moving. The largest explosive eruptions we have on Earth are called Plinian eruptions. This is named after Pliny the Younger, who made the first observations of the 79 AD eruption of Vesuvius in Italy. And you're probably very well aware of this eruption, but killed thousands of people and buried the Roman towns of Herculaneum and Pompeii. Next slide, please. And these very large explosive eruptions are the main eruptions we need to think about in terms of climatic impacts. So these Plinian eruptions send columns up to 45 kilometers or more. The Tonga eruption recently broke that record. I think the overshoot plume top was around 53 kilometers high into the atmosphere. And these columns are generally sustained for hours to days. They made up of different regions. So we have the jet region at the base, which is sustained by kinetic momentum from gas expansion. We then have the convective region, where the plume has entrained enough air from the surroundings to become buoyant. We then have the umbrella region, where the plume spreads laterally because it reaches a level of neutral buoyancy with the atmosphere. So it's no longer favorable for it to rise higher, so it then spreads laterally. Next slide, please. This is an example of where we have tracked a volcanic plume from space. This is using satellites, and you can see the eruption begins over on the right-hand side at Pinatubo, and then travels around the globe. It actually traveled around the globe several times. And the 1991 Pinatubo eruption was probably, well, it was probably one of the first and most influential eruptions within modern satellite monitoring era. So we learned a lot about the climatic impact of these largest volcanic eruptions from Pinatubo, because we developed the capacity to be able to measure in space how much aerosol was being created, how long the SO2 was remaining resident, and then looking at how this had affected global temperatures over the coming years. Next slide, please. So how eruptions impact on climate. This is a short 101. Essentially, I've mentioned that SO2 gas is released. This is the main gas we need to think about. CO2 is also a very important greenhouse gas, but it's so abundant in our atmosphere normally that individual volcanic eruptions generally produce negligible effects on the carbon dioxide. So let's think for the moment about SO2. Large volcanic eruptions produce cooling at the Earth's surface and warming up in the stratosphere. And this can generally persist for 2 to 3 years after a major eruption. The main reaction is this conversion of SO2 gas into what we call sulfate aerosol particles. So it goes from a gas to a particle. And these aerosol particles have very long residence times. And they act to cool the troposphere, so the area of atmosphere around us at the Earth's surface, by scattering radiation back into space. So it doesn't get a chance to come down and warm the surface of the planet. They also absorb radiation being re-radiated back from the Earth's surface. So this is how we get the cooling at the Earth's surface and warming in the stratosphere. If you look at records of temperature through time, you can see the long-term trend of warming temperatures, which is the anthropogenic impact. But then you can also see these very transient dips in temperature lasting around 2 to 3 years. And these can be attributed to major volcanic events. If volcanoes erupt, but the plume doesn't reach the stratosphere, it remains in the troposphere, then the lifetime of SO2 and sulfate is much reduced. We're talking 1 to 3 weeks. Here, the major hazard is reactions between the sulfate aerosol particles and water, as this can form acid rain. Right, next slide, please. One of the best examples of the climatic impacts of large explosive eruptions was Tambora in 1816, which produced the year without a summer. Now, in Europe, temperatures were decreased by 2 to 3 degrees, which may not sound like a lot, but 2 to 3 degrees can represent the difference between your crops failing or being successful. So there was huge food shortages this summer. And also, I quite like this, is that this is the painting by W. Turner, and you can see in all these paintings from this era, the skies are reds and oranges and beautiful shades of autumnal colors, not your clear blue skies. And this is most likely the effect of the aerosol content in the atmosphere, because the scattering effect of incoming solar radiation, it creates these nice colors that you see here. So it's the optical effect of having lots of particles in the atmosphere, is you can get these beautiful sunsets. Right, next slide, please. The final thing I want to talk about, and then I promise there'll be plenty of time for questions, is the opposite end of the scale, is the less explosive eruptions that produce lava flows. So the example I'm going to discuss is the 2018 eruption of Kilauea. You can see on the left here a map of where the lava flows went. They covered a large area of the lower east rift zone of Hawaii. Next slide, please. From these less explosive eruptions, the most important thing we need to think about is the air pollution hazard in terms of the chemical hazard from the volcano. So SO2 gas is the most widely recognized air pollutant, but as I mentioned, eruptions also emit metallic elements like lead and copper into the atmosphere. So if you look on the graph at the bottom, we've got some major metallic species from copper, cadmium, arsenic, and then we show the daily emissions in kilograms per day on the y-axis. We've compared several major lava flow producing eruptions in the colors to the output of these metals from nations like the UK, Germany, USA, and China. And although we've got a log scale on the y-axis, so small changes represent, so small distances represent big differences, that's how log scales work. We can see that in some cases, and for particular metals, volcanoes are releasing on the order of or greater than the similar metal emissions from anthropogenic and industrial activities. So this is definitely an area of research that needs a little bit more understanding. It's really important to know how these elements interact with our environment, particularly during these long-lived lava flow producing eruptions. Next slide, please. So during the 2018 eruption of Kilauea, we had the eruption on the eastern side of the big island of Hawaii. And I've shown here two images on the top from Kona, which is on the opposite side of the island. The one on the left is during the eruption, and the one on the right is 2 months after the eruption ends. I don't think any of you will argue that the air quality improved dramatically once the eruption was over. I was actually fortunate enough to be on site responding to this eruption, and I can confirm that the air quality was truly terrible over on the Kona side. You could really feel it after a couple of hours of being outside. You could really feel it in the back of your throat. The photo at the bottom shows what it was like close to the source, and I often show this image because I think it really captures just how the gas plume can be influencing. This looks rather menacing. You've got the gases rising above the fissure, being transported in these huge billowing pyro clouds, and then you can already see some of the gases being deposited in communities close to the source. Right, next slide, please. If we look at some of the air quality monitoring stations around the island, there are well-established health guidelines for what is a safe limit of particulate material to be exposed to. We call this PM 2.5. So any particle smaller than 2.5 microns, anything that can be easily inhaled, basically. And we can see that most of the time, this runs from 2010 through to the eruption is highlighted in the blue shaded region. Most of the time, the gases are well below the safe limit. I should mention that before this eruption, Kilauea is producing, it's one of those passive emitters. So it's releasing a small amount of gas all the time. But then during the eruption, the levels of PM 2.5 escalated dramatically. Next slide, please. So we started having to think about how often the health limits were being exceeded and whether any recommendations needed to be made for people to, for example, remain in their homes under particular weather conditions. This eruption lasted 3 months. So this was enough time for some of the measurements made earlier in the eruption to actually inform management procedures towards the end of the eruption. What you can see in the graph on the left-hand side is the number of days on which the health limits for SO2 gas and particulate matter was exceeded in particular locations. So you can see upwind of the eruption, the air quality was fine. The health limit was never exceeded. Close to source, we had many exceedances in terms of SO2. And then further away, once we got round to the far side of the island, we started to see exceedances for particulate matter. But interestingly, not close to source. So remember this. Next slide, please. And this is all about this gas to aerosol conversion again, but on a much smaller scale than we discussed in relation to climate. So the plume dispersal is strongly controlled by the regional wind field. And the reason why we had such poor air quality on the far side of the island from the eruption was because the trade winds were taking the gas plume, circling it back round in the leeward side of the island, and it was remaining stagnant over on the westward side. So actually the air quality was being cleaned effectively by the trade winds near to the eruption, and then it was hanging around on the western side. What we can see from the figure on the right, the colour of the gas plume corresponds to the proportion of the total sulphur as SO2 gas relative to particulate aerosol. And we can see that over the timescale of around 20 hours, as the plume moves from the eruption side round to the Kona side, we get about 20% conversion of the SO2 into sulfate aerosol. So this explains how the nature of the hazard and the necessary response measures need to change downwind of the eruption site. And even 100 kilometers away from the eruption, we need to be thinking about the chemical hazards that volcanoes are having on our environment. Next slide, please. The final thing I'll mention, which is projects that I'm actively working on at the moment, is understanding how these metallic trace elements are entering our environment from the plumes from volcanoes. This can either be by deposition by rainfall. So these metals will preferentially dissolve into rainfall droplets. And this is particularly hazardous in parts of the world that rely on rainwater for their drinking water. And also parts of the world that rely on rainwater for irrigation, as these metals can bioaccumulate in crops and soils and enter the ecosystems. So this is a hot topic that I'm thinking a lot about at the moment. Next slide, please. All right, so that was a whistle-stop tour through a few examples of how we can use chemistry to understand volcanic eruptions. Volcanoes are essential to how our planet has evolved its surface environment and atmosphere, but we mustn't forget they pose a risk to society and our environment. Chemistry is so much more than test tubes and titration experiments, and we can really use it to solve big picture questions in earth sciences. So I realized that went on a little bit more than I expected to, but I hope you found it interesting. Happy to answer any questions that you may have.